Today's lecture is on special theory of relativity. First of all, I will discuss what is the limitation of Newtonian mechanics and why we introduce special theory of relativity. We all know that we can send a signal through free space from one point to another point using a beam of light or some other electromagnetic radiation, such as radio wave. And the measured speed of light is in free space 3 into 10 to the power 8 meter per second, and this is the most accepted value of this is the most accepted value of light. All the speed of other particle can be compared with the speed of light in free space. Now we will discuss that is the difference between macroscopic world and microscopic world. Macroscopic world includes things that are very large in dimension and visible with naked eyes. In the macroscopic world, the speed of a particle or a mechanical wave with respect to any observer is always much less than c. We can cite some example. For example, an artificial satellite when revolves around the earth with a speed is nearly about 8,000 meters per second. And when we compare it with the velocity of the light in free space, this velocity becomes v by c is nearly equal to 0.000027, and this is very less compared to the velocity of light in free space. Another example is the velocity of sound wave in air. Velocity of sound wave in air is 332 meters per second, and when we take the ratio of v by c, in this case this is become 0.000010, and this is also very less than c. In this macroscopic environment, when velocity of any moving system is much less than velocity of light in free space, we can use Newtonian mechanics developed on Newton's 3 laws of motion, and then we get an idea about space and time. There is another world that is called microscopic world. In this world, we consider the building blocks of matter, that is the atoms and the molecules. They are very large in dimension. They are not visible with the naked eyes. In this macroscopic world, unlike the macroscopic world, particle may move with a speed very close to the velocity of light in free space. As for example, when an electron of mass m and charge e is accelerated through a potential difference v, its velocity is based on Newtonian mechanics is given by v equal root over 2 e v by m, and I am showing this derivation in blackboard. Suppose charge of the electron is the initial velocity is 0 and final velocity is small v, and mass of the electron is m, and change in kinetic energy equal to half mv square. This is the final kinetic energy minus initial kinetic energy. Initial velocity is 0, so this is equal to half mv square, and a capital V is the potential difference then work done W will be E into V. Therefore, half mv square equal to E into V, and therefore V equal to root over 2 capital E V by m. Now experimentally, when we take the potential difference V equal to 10 to the power 10 million volt, that is 10 to the power 6 volt, and charge of electron E equal to 1.6 into 10 to the power minus 19 coulomb, and mass of the electron M equal to 9.1 10 to the power minus 31 kg, and putting this value we get the velocity V equal to 2.99 into 10 to the power 8 meter per second. And when we divided this velocity by velocity of light in free space, we get V by C equal to 0.9988, which is very close to velocity 1. So from this expression, it is obvious that if potential V, the potential difference capital V, is increased by 4 times, that is previously it was 10 million electron volt, now it will be 40 million electron volt. Then if capital V is increased 4 times, then velocity will be increased 2 times. But theoretically velocity will be 2 times. But experimentally, it is found that velocity become 0.9988 from 9998. So experimental result and theoretical result does not match in the microscopic environment. So in the microscopic environment, Newtonian mechanics does not work well, and we require a new mechanics which is called the special theory of relativity, which is applicable in the all range of velocity from low range of velocity to high range of velocity. To develop the special theory of relativity, to discuss the development of special theory of relativity, we require the concept of wave. So first of all, very little introduction. What is wave? A wave is a disturbance that can propagate through a medium and transport energy from the location of the source where the disturbance was created to another location with the actual movement of the particles of the medium. There is another way of transporting of energy from one place to another place, which is when the particle itself carry energy. The position of the particle change, but when the wave transport energy, this position of the particle of the medium does not change. And the wave can be of 2 types. One is mechanical wave, another is electromagnetic wave. Mechanical wave requires a material medium to travel. Mechanical wave cannot propagate through vacuum. Another wave is electromagnetic wave. Electromagnetic wave develop when electric field and magnetic field vibrate perpendicularly. Then electromagnetic wave propagate perpendicular to both electric field and magnetic field. And electromagnetic wave are different spectrum, and according to the increasing order of energy, it can be divided as radio waves, microwaves, infrared, light, ultraviolet, X-ray, gamma ray. Gamma ray wavelength is smallest and it has maximum energy of electromagnetic spectrum. And unlike the mechanical wave can travel only through medium. It cannot propagate through vacuum. But electromagnetic wave can travel through a material medium and also through the free space. Now, all parts of electromagnetic wave from radio wave to gamma wave propagate through vacuum with the same speed c equal to 3 into 10 to the power 8 meter per second. Now we introduce the Galilean transformation. What is Galilean transformation? Why do we introduce Galilean transformation? The special theory of relativity basically describes the description of the same event with respect to different observer, different inertial frame. So we are considering two inertial frame. Another inertial frame is S and another inertial frame is S dash frame. We drawing this figure in the blackboard. S and S dash are two inertial frame. Initially, origin O of S frame and origin O prime of S dash frame are overlapped. Axis of S prime frame are overlapped. And all the time scale, all the length scale of S and S dash prime are same. Then S frame is moving, S dash frame is moving with respect to S frame with velocity V along common X dash frame. Suppose P is a particular point. Suppose P is a particular point. P is a particular point in space. With respect to S frame, the coordinates of the event P are x, y, z and time t, and with respect to S dash frame, coordinates of the same event are x prime, y prime, z prime and t prime. As a velocity, so the relation between the x prime, y prime, z prime, t prime and x, y, z and t are x prime equal to x minus vt, y prime equal to y, z prime equal to z, t prime equal to t. This transformation relation x prime equal to x minus vt, y prime equal to y, z prime equal to z and t prime equal to t. This is the your vt distance. If this is the point P, this will be x prime and this will be or x. So x prime equal to x minus vt and y prime, z prime, y, z axes are parallel. So y prime will be y, z prime equal to z, t prime equal to t as the velocity is along x axis. This transformation is called Galilean transformation. In the Galilean transformation, t prime equal to t. This is the absolute nature of time. The time is same for all the observer and independent of any particular frame of reference. Here S dash frame is moving with respect to velocity v along S frame. So x prime equal to x minus vt, y prime equal to y, z prime equal to z and t prime equal to t. So these are the Galilean transformation. If we reverse back the process, then we can say that S frame is moving with respect to S dash frame with velocity minus v. Then we can write x equal to x prime plus vt prime, y equal to y prime, z equal to z prime and t equal to t prime. These four equations are called inverse Galilean transformation. And the two set of transformation are conjugate to each other. Here for simplicity, without affecting any physical result, we assume that velocity of S and S prime is common x prime axis. If velocity is along arbitrary direction, say arbitrary direction is velocity is v, then this transformation relation can be written as x prime equal to x minus vxt, y prime equal to y, y prime equal to y minus vyt, z prime equal to z minus vzt, and obviously time will be same, t prime equal to t. Similarly, inverse transformation relation will be x equal to x prime plus vx prime t, y equal to y prime plus vyt, and z equal to z prime plus vzt and t equal to t prime. These are inverse Galilean transformation relations. In vectorial form we can write r vector equal to r prime vector equal to r vector minus v vector t, or inverse. In case of inverse, we can write r vector equal to r prime vector plus v vector t. This is our Galilean transformation relation. Now some important points from the Galilean transformation relation. We want to discuss some important points about Galilean transformation. Let two events occur at points P and Q in space at two different instants of time. The space-time coordinate of the P with respect to the observer in S and S dash frame. So the time interval between the occurrence of these two events is absolute. The time interval between the two events occur in a particular point, and we measure the time interval with respect to an observer in S frame, and respect to another observer in S dash frame, then time interval with respect to observer in S frame and the time interval with respect to an observer in S dash frame will be same. The time interval between two events with respect to two observer, one is S dash frame and another is S dash frame, will be equal. Another important point is that the length interval, if we measure the length interval between two particular points where the two events occur, then length interval between the 2 points with respect to 2 observers, one is from S observer, another is S dash frame observer, this will be also same. And this is totally independent of the velocity of the S and S dash frame. Another important point is that if an observer is moving, and we want to measure the length of the moving observer, then we have to take the endpoint coordinates of the two endpoints, space coordinates of the two endpoints, the same instant of time. Space coordinate of the endpoints has to be taken the same instant of time to get the length of a moving observer. Another important point is that in the Galilean transformation Newtonian mechanics, mass is constant, and we already proved that length interval, time interval, they are also constant. There are 3 basic quantities: mass, length, and time interval. They are remain unaffected by Galilean transformation. They are independent of the relative motion between the different inertial frame. And there is a limitation of Galilean transformation. Galilean transformation equation produce accurate result when the velocities of the bodies involved are very, very small compared to the light in free space. Now I want to mention a few words about physical event. A physical event is something that can happen independently of the reference frame used to describe it. So a physical event can be described with respect to an S frame or also with respect to an S dash frame. Suppose we consider a collision between two particles occurring at a particular point in space at an instant of time. And this is an example of an event. This event can be described by 3 position numbers x, y, z and the time t with respect to a frame of reference. This position number x, y, z and the time t all together are called 4th space-time measurement of that event with respect to a particular frame of reference. The explosion of a firecracker at a particular specific position is also an example of an event. This same event can be described with respect to different inertial frames. And when we describe the same event with respect to different inertial frame, the 4 space-time number will be different, may be different or it may be same. Generally, it will be different. This event collision can be between 2 particles may occur in a laboratory on the earth, and also this event can be described with respect to an airplane flying over it. Here the laboratory on the earth is our S frame and the airplane which is flying over it is our S dash frame. And special theory of relativity describes the events by an observer in only inertial frame, and general theory of relativity introduced by Einstein in 1917 deals with all frame of reference which include non-inertial frames also. And another point to mention here, what is inertial frame and non-inertial frame. Inertial frame remains at rest or moves with uniform velocity, but non-inertial frames move with acceleration. Now we come to the another point, another topic, that is called Newtonian relativity. So this is our Galilean transformation relation: x prime equal to x minus vt, y prime equal to y, z prime equal to z, t prime equal to. These are the Galilean transformation, and x equal to x prime plus bt prime, y equal to y prime, z equal to z prime, t equal to t prime. These are inverse Galilean transformation. And t prime equal to t, here also t equal to t prime, that is time is absolute. It is same in all the observer in S frame and S dash frame. When we take the derivative of this equation dx prime by dt, this will be equal to dx by dt minus v, or vx prime, this will be vx minus v. Or suppose this is ux prime equal to ux minus v. Ux or ux prime is the velocity of the particle in S frame and S dash frame. Similarly, uy prime equal to uy, uz prime equal to uz. And from this equation we also get ux equal to ux prime plus v uy equal to uy prime and uz equal to uz prime. As we have assumed that the velocity of S and S dash frame is along common x prime axis, so velocity of along y and z axis remain unaffected. But the velocity of the particle in S and S dash frame is different, and ux prime equal to ex minus v, ux equal to ex prime plus v. This set of equation is called velocity transformation equations. And when we take the derivative of this equation, we get dux prime by dt. This is equal to dux by dt, this minus 0 because velocity is constant, or ax prime equal to ax. Similarly, from this equation, ay prime equal to ay, and from this equation, az prime equal to az. Similarly, from this set of equation, we will get ax equal to ax prime, ay equal to ay prime, az equal to az prime. So, velocities of the particular particle in S and S dash frame are different. They are by under Galilean transformations, but accelerations are same. Okay. So ax, ay, az are the acceleration of the particle in S frame, and ax prime, ay prime, az prime are the acceleration of the particle in S dash frame. And again, mass m, we already have mentioned that mass m is invariant under Galilean transformation. So we multiply the mass m and acceleration, we get that m ax prime equal to m ax, m ay prime equal to m ay, m az prime equal to m az. That is f x prime equal to fx, f y prime equal to fy, f z prime equal to fz. So the force acting on the particles are same in both in S frame and S dash frame. As the force are same, so all the mechanical laws will be same for the particle in both in S and S dash frames. So we can conclude that the acceleration of a particle is the same for all inertial observer moving with constant velocity relative to one another. In classical mechanics, in classical Newtonian mechanics, the mass m is also not affected by the motion of the reference frame. Hence, the force is also the same for all inertial observer as we have derived here. And the force of the particle are measured by the observer as respective. So, Newton's laws of motion and the equation of motion of particle will be exactly same, invariant in all inertial frame. And it is also said that Newton's law are invariant under Galilean transformations. And in mechanics, all the conservation principles like principle of energy, linear momentum, angular momentum, etc., all can be derived from Newton's law. Thus, we can conclude that the laws of mechanics are the same in all inertial frames under Galilean transformation. This is a very important point, that all the laws of mechanics, are same in are the same under Galilean transformation. So far we have what we have discussed. We have discussed the limitations of Newtonian mechanics in microscopic world. To overcome this limitation, we have introduced special theory of relativity, and special theory of relativity basically describes the same event, same phenomena with respect to different observer. So we have considered two inertial observer. One is S frame at rest, another inertial frame which is moving with velocity v with respect to S frame. And under this Galilean transformation, we consider the Galilean transformation, which basically is the transformation between the coordinates of the same point with respect to S frame and respect to S dash frame. And under the Galilean transformation, we have shown that the laws of mechanics will be same. All laws of mechanics will be same under Galilean transformation. They are invariant. And no mechanical experiment carried out entirely in one inertial frame can tell the observer whether the frame is at rest or in uniform translational motion. We cannot detect absolute velocity through empty space or absolute rest frame by any mechanical means. The conclusion is that all inertial frame in relative motion with constant velocity are equivalent. No preferred inertial frame exists as far as mechanics is concerned. This is known as Newtonian relativity. And Galileo, long before Newton, stated this principle of relativity in classical mechanics. Hence, Newtonian relativity is also known as Galilean relativity, and the set of equations also are known as Galilean transformation equation. Now we come to the important point, electromagnetism under Galilean transformation. And electromagnetism under Galilean transformation led to the development of special theory of relativity. We have already discussed that there are two types of wave. One is mechanical wave and another is electromagnetic waves. Now we consider the transformation of wave equations under Galilean transformation. We have already shown that laws of mechanics, Newton's laws of motion, are invariant under Galilean transformation. But the transformation wave equation, from the transformation wave equation, it is important to note that no wave equation does not get back the same form under Galilean transformation like the laws of mechanics. But although the wave equation does not get back the same form, there is no problem in the mechanical waves, because mechanical wave can propagate only through material medium. It cannot propagate through vacuum. So when a medium is at rest and the wave is propagating through it with a definite velocity Vm, depending on the nature of the medium. Now, if the medium of the observer in the medium moves towards the sound wave with a sound wave is a mechanical wave with a velocity v, then the velocity of the mechanical wave will be Vm minus v with respect to the observer. And if the medium or of the observer in the medium moves in the opposite direction of the sound wave with the same velocity, then the velocity of the wave will be Vm plus v with respect to the observer. This fact is according to the Galilean transformation and has been confirmed experimentally. Although the equation which governs the mechanical wave motion is not invariant under Galilean transformation, there is no conceptual problem in mechanical wave motion, because mechanical wave does not propagate through vacuum. Now the problem came into picture when the electromagnetic theory was developed. From this theory it flows that electromagnetic wave, as for example light, can propagate through vacuum with velocity c equal to 3 into 10 to the power 8 meter second inverse. Historically, when special theory of relativity is developed in 1905, people could not think about a wave phenomena without a medium. So it was believed that electromagnetic disturbance also could not propagate through the empty space vacuum. So the medium of the electromagnetic wave propagation was given the name ether with some unusual properties, because it is totally undetectable. So we assume that the ether has zero density, that is massless. It has perfect transparency, that is, it is undetectable. And at the same time, to sustain high speed waves, it should be highly glass tips. The ether was assumed to pervade all the space. And we take the ether frame as an inertial frame H at rest. An electromagnetic wave, when travels with the speed c to the right with respect to the observer to this medium. The observer in S frame measures the speed of light in exactly c, and S dash frame moves with a constant velocity v through the ether with respect to S frame to the light. So, according to Galilean velocity transformation equation, the observer in S dash frame moving at a constant velocity v with respect to this ether frame would measure the speed of light c minus v when the motion of the observer in S dash frame and the motion of the wave are in the same direction, and c plus v when the motion of the observer in S dash frame and motion of the wave are c plus v when the motion of the observer and motion of the wave are in opposite direction. So, the speed of light wave in so-called ether is not an invariant quantity under Galilean transformation, and there is one and only unique inertial frame with so-called ether at rest in which the measured speed of light is exactly c. So, in previous slide we have shown that in ether medium velocity of light is not invariant. It is when the ether medium is at rest, then the velocity of light is exactly c. But when the ether medium, when the observer is moving with respect to the ether medium, then with respect to the observer, velocity of light is in one case is c minus v, and in another case it is c plus v. And there are some Maxwell's equation of electromagnetism. This is a Gauss law in electrostatics, Gauss law in magnetostatics, Faraday's law of induction, and Ampere's law. And all the laws of Maxwell's equation in Gaussian unit contain the constant c. And the propagation of electromagnetic wave through a medium is governed by equation known as electromagnetic wave equation. And the electromagnetic wave equation can be derived from the Maxwell's equation. As Maxwell equation, wave equation also contains the constant c, where c is the velocity of light in vacuum. And we have already observed that this velocity of light in vacuum is different for different inertial observer according to Galilean transformation. Again in the wave equation there is some operator known as gradient operator. And the gradient operator in mathematical form, gradient operator. Gradient operator. So gradient operator is not the same in true frame S and S dash as the coordinate are related by Galilean transformation equations. Thus Maxwell's equation as well as wave equation are not preserved in form that is not invariant under Galilean transformation, because the velocity of light which appear explicitly in Maxwell's wave equation, in the Maxwell's equation, in the wave equation governing the wave motion, and also there is gradient operator, and gradient operator includes the coordinate x, y and z, and they are related by the Galilean transformation. Due to these two reasons, the Maxwell's equation and wave equation are not preserved in form, they are not invariant under Galilean transformation. So all the inertial frame are not equivalent from electrodynamics point of view under Galilean transformation. That is, Newtonian relativity does not hold for the laws of electromagnetism. But laws of mechanics are invariant under Galilean transformation. Very, very important point. Laws of mechanics are invariant under Galilean transformation, but laws of electromagnetism are not invariant under Galilean transformation. It is also important to mention that the speed of a material particle is also not the same for all inertial observer related by Galilean transformation. But the acceleration of particle is an invariant quantity in Galilean transformation, and Newton's equation of motion does not contain velocity explicitly. It is directly related to the acceleration of the particle. So, Newton's laws of motion, in sharp contrast to Maxwell's equation or wave equation, are invariant under Galilean transformation, but Maxwell's equation, wave equation are not invariant under Galilean transformation. Now we come to another important topic, that is called Michelson-Morley experiment. The famous Michelson-Morley experiment was performed to locate the absolute frame, a single unique system named ether frame, in which the speed of light is c, the value predicted from electromagnetic theory. A. Michelson first alone performed the experiment in 1881, and then in collaboration with E. W. Morley in 1887 carried out the same experiment more precisely. The investigation laid down the experimental foundations of relativity theory. This is a very, very important experiment in the development of relativity theory, special theory of relativity. The Michelson's interferometer. This is a picture of Michelson interferometer. We draw this picture in the blackboard. First, we draw this picture in the blackboard. Observe carefully. This is the picture of the Michelson interferometer. The instrument is used in the experiment was a very sensitive interferometer invented by Michelson-Morley. This is known as the Michelson interferometer. It consists of two optically plane mirror, M1 and M2, highly silvered on front surface, and another and their planes are kept mutually perpendicular. A monochromatic beam of light from an extended source S fixed in laboratory with respect to this instrument is made parallel by the lens, and then is incident at 45 degrees on the half silvered plane glass plate M. M divides the incident beam into two coherent beams of equal amplitude, a reflected beam M2 and a transmitted beam M1 by partial reflection and transmission at the rear side of M. So this is the picture of the Michelson interferometer. This is the source. Picture 7.2 is the diagram of the Michelson's interferometer, which I described earlier, and picture 7.3 is used to calculate the path difference between two interfering beams. The transmitted beam M1 is reflected normally back to M by mirror M1, and the beam M2 is reflected normally by M2 back to M. Then the returning beam M1 is partially reflected by M, and the returning beam M2 is partially transmitted through M. The two returning beams reunite at a point on the half silver phase of M to produce interference fringes, which are observed through the telescope capital T. It is clear that the wave reflected from M2 crosses the glass plate M thrice, while the wave reflected from M1 traverses M only once. And to compensate for the extra path difference by M2 in going through M and back on reflection from M2, a compensating parallel glass plate identical to M called the compensator C is interposed between capital M and capital M1. The interference will be constructive or destructive depending on the phase difference or path difference of the two interfering beams. If the mirror M1 and M2 are exactly perpendicular to each other, the interference fringes would be concentric circles, but in actual experiment, the angle between the mirror are kept slightly smaller than 90 degrees, so that the fringe system will be consist of nearly parallel lines. Now we come to the theoretical basis of the experiment. This is the theoretical basis of experiment. Michelson's interferometer experiment was performed to locate the ether frame in which velocity of light is c. And if we assume that the ether exists, then the spinning and rotating earth, which is object, moves through it with a velocity v relative to it. And an observer on the would sense an ether wind in the opposite direction with a velocity minus v. The experiment is conducted on the Earth's surface and the Michelson interferometer is fixed on the Earth. We consider the Earth is fixed with respect to the Sun and the ether with this interferometer moves through the ether with a speed in different direction and in different season. The Earth moves along in its nearly circular orbit about the Sun and reverse the direction of its velocity every 6 months. We will neglect the spin motion of the Earth, then v will be equal to the Earth orbital speed. Say v equal to 3 into 10 to the power 4 meter second inverse. So that v by c equal to 3 into 10 to the power 4 divided by 3 into 10 to the power 8, that is nearly equal to 10 to the power minus 4. v by c equal to 10 to the power minus 4. Now we will compute the phase difference or path difference between two beams M1 and MM2. The phase difference arises due to different path length traveled and also from the different speed of light with respect to the instrument because of the ether wind v. We assume that the length of the two arms MM1 and MM2 the interferometer equal, say MM1 and MM2 is small d. If the arm MM1 is parallel to the direction of the earth motion, the velocity of light is c minus v in moving from M to M1 and c plus v for return journey from M1 to M. Now we will compute the phase difference between the beams MM1 and MM2. Assuming the earth MM1 of the interferometer parallel to the direction of the earth motion, the upstream velocity of light is c minus v in moving from capital M to capital M1 with respect to the apparatus, and a downstream speed of light is c plus v for the return journey from M1 to M with respect to the same apparatus. So the time beam M1 takes to travel from M to M1 and back is t equal to d minus c by v plus d plus c by v. That is, after simplification, this becomes 2d by c 1 plus v square by c square. Similarly for the beam MM2, we get 2d, we get corresponding time with respect to the ether frame is t2 equal to 2d by c 1 plus v square by 2 c square, and both t1 and t2 increase the transit time over the case when v is equal to 0, and they are in the same direction. So difference in 2 times delta t1 equal to t1 minus t2, this is 2d by c 1 plus v square by c square minus 2d by c 1 plus v square by 2 c square, 2d by c 1 plus v square by c square minus 1 minus v square by 2 c square. After simplification, this become d by c v square by c square. Now the instrument is rotated through 90 degree, and so the arm MM1 will be cross stream length and MM2 will be downstream length. The same analysis as given above gives rise the transit time difference for two beams after rotation as delta t2 equal to 2d by c 1 plus v square by c square minus 2d by c 1 plus v square by c square, and after simplification this become minus d by c plus v square by c square. So difference between two time difference delta t1 and delta t2 due to the rotation of the instrument is delta t equal to 2d by c v square by c square, and this delta t is non-zero, and non-zero value of delta t implies that rotation changes the phase relationship between the arms MM1 and MM2, and hence there should a cause of shift in the fringe pattern. And if the optical path difference between the beams changes by one wavelength, then there will be a shift of one fringe across the cross wire of the telescope. Just a few words, what is the optical path difference? When a light travels through a medium with refractive index mu and it covers a distance L, then optical path difference will be mu into L. So if the optical path difference between the beams changes by one wavelength, then there will be shift of one fringe across the cross wire of the telescope. If delta n is the number of fringe shift across the crosswire of the telescope due to rotation of the apparatus in time delta t, then the delta n will be c delta t. This is the actual time divided by wavelength lambda. For lambda wavelength change shift, for shift of lambda wavelength, there will be one fringe shift. So c delta t is the total distance. The total distance divided by lambda, this will give the total number of shift delta n. So this will be equal to c by lambda 2d by c v by c square. We have put the value of delta t. So this is 2d by lambda v square by c square. And Michelson-Morley were able to obtain path difference 2d equal to 20 meter. He has used the wavelength lambda equal to 550 angstrom, and putting these all the values v, c, d and lambda, we get delta n equal to 0.04. So full length of a fringe shift is expected in Michelson's interferometer. Not exactly one fringe shift. One fringe shift, one fourth should be observed in Michelson-Morley experiment. Should be detected. And the Michelson's interferometer was very sensitive, and also the experimental arrangement was made in such a way that a shift as small as 1 by 100 of a fringe definitely could have been detected. If there is a fringe shift, then 1 by 100 of a fringe shift could have been detected. The instrument was so sensitive and the experimental arrangement was made in such a way. And observations in day and night and during all the season of the year ended in a negative result. No fringe shift whatsoever was observed. So there is no fringe shift at all. The earth is with respect to an absolute frame is 0. So there is no ether wind. The null result rules out that there is no absolute frame. If we look at this expression delta n, again we write in the blackboard. Delta n equal to 2d by lambda v square by c square. As delta n equal to 0, obviously v square will be equal to 0 because d not equal to 0, lambda not equal to 0 and c not equal to 0. Is v is 0. So when we have already mentioned that there velocity of light in the ether medium was c plus v and c minus v. So this will only equal to c. So from the Michelson interferometer, it was confirmed that there is no ether medium. Then the measure speed of light in free space is the same, that is c for all direction in every inertial system in contradictory of the Galilean velocity transformation. The measure speed of light will not depend on the motion of the observer and its source. It also does not depend on the motion of the observer and also on the motion of the source. All the inertial system will be equivalent for a propagation of light in vacuum. There will be no experimental evidence on any types to indicate the existence of a unique inertial system, that is the ether frame in which the speed of light is c. From the Michelson-Morley experiment, we get a conclusion that there is no ether frame at rest. There is no ether frame. There is no existence of ether frame. And from the inference of Michelson interferometer experiment, we come in postulates of special theory of relativity. The special theory of relativity is based on these two postulates. The null result of Michelson-Morley experiment was such a surprise blow to the physicists that the same experiment was repeated by many workers over a 50-year period, and also many similar experiments, both electrical and optical, were performed, but all ended in a negative result. There was no experimental basis of any types, either mechanical or electrical, for the idea of ether, a preferred inertial frame of reference. The speed of light, that is electromagnetic radiation in free space, is the same in all inertial systems, independent of relative motion of the source and the observer. The constancy of the speed of light in all inertial system in relative uniform translational is very much incompatible with the Galilean transmission relativity. Then one assume that a new relativity principle should exist, which is valid both for mechanics and electrodynamics. But we are forced by experiment to conclude that the laws of electrodynamics are correct and do not need any modification. And also the speed of light, electromagnetic radiation is the same in all inertial system. So, but Newtonian mechanics fails at high speed, as we have mentioned in our introduction, when we accelerate an electron through a potential difference. So, at Newtonian mechanics fails at high speed, one can try to reformulate the mechanical law. Then the classical electromagnetism, the new mechanics will be invariant under this new transformation law. These radical changes were brought about by Einstein in 1915. And after through analysis of experimental facts and proposed the special theory of relativity based on the following two postulates. The postulates are all the laws of physics are the same in all inertial system in uniform relative translational motion or at rest. No preferred inertial system exists. This is the principle of relativity. All the laws, first postulate of relativity, all the laws of physics are the same in all inertial system in uniform translational motion or at rest. Or in our case, these are S frame and S dash frame. S frame was at rest and S dash frame was moving with respect to S frame with velocity v. So all both S and S frame are same. The speed of light in free space we mentioned that this is free space. Speed of light in free space has the same value c in all inertial system in all direction and independent of the motion of the observer and on its source. This is the principle of constancy of the speed of light. And in relativity theory, both the space and time are variables. They are both a coordinate, both 3 space coordinate and 1 time coordinate. They are 4 space-time coordinates. Now, all the experimental observation have been found to agree with the theory of relativity. Now, all the prediction of relativity theory have been confirmed by experiment. As the Galilean transformation equation are not correct in relativity principle both for classical Newtonian mechanics and for the laws of electrodynamics. Newton's laws of motion are invariant, but Maxwell's equation as well as wave equation are not invariant under Galilean transformation. Under Galilean transformation, all the inertial frames are equivalent from mechanical point of view, but they are not equivalent from electrodynamical point of view. So, Einstein replaced Galilean transformation by a new set of relations developed by Lorentz called Lorentz transformation equation. This equation of transformation between two uniformly moving inertial system keep the velocity of light constant, and Lorentz already had shown Maxwell's equation remain invariant under Lorentz transformation equation. Lorentz regarded this transformation law as a mathematical transformation, but he did not give any physical significance. Einstein independently developed Lorentz transformation equation and gave their physical interpretation. Then Newton's laws and perhaps other commonly accepted laws of physics which are not invariant under Lorentz transformation. They are invariant under Galilean transformation, but they are not invariant under Lorentz transformation, must be reformulated in such a way that they remain invariant under Lorentz transformation. And the new laws will reduce to the old ones for velocities much less than that of light. For in that range, both the Galilean transformation and the Newton's law are at least approximately correct. Now we come to the derivation of Lorentz transformation. Like Galilean transformation, there is also same. We are considering two inertial frame. One is S, another is S dash frame. S frame is at rest and S dash frame is moving with constant velocity v with respect to S frame. An event occurs at a particular point in space. The coordinate of the point P with respect to S frame is x, y, z. They are the space coordinate of the point and T is the time coordinate. And similarly, with respect to the observer in S dash frame, x prime, y prime, z prime are the time coordinate, space time coordinate of the event, and t prime is the time coordinate of the event with respect to the observer in S dash frame. And we'll derive the functional relation between these two set of space time coordinate based on the fundamental postulates of relativity assuming that space and time are homogeneous. And also the previous assumption, unlike the Galilean transformation, also takes some assumptions. Initially, the clocks of S and S prime synchronize at time t and t prime equal to 0. The origin O and O prime of S and S prime coincided. The three set of axes are overlapped, and without affecting any physical principle involved, we assume that relative motion of S dash with respect to S prime along common x prime axis in the positive x prime direction, keeping y prime, z prime of the both prime remain parallel to each other. As space-time is isotropic, this assumption does not impose any fundamental restriction on our result. As the space-time is isotropic, we can take velocity of S dash frame in any arbitrary direction with respect to S dash S frame. We also assume that at the time t equal to 0, a light wave leaves the origin of S and the origin of S dash frame, because at that moment two origins coincide. Now, from the postulate of the principle of constancy of the speed of light, the wave propagates with a speed c in all directions in both S and S dash frame. Again, according to the principle of relativity, if the wavefront of light at time t in S frame is a sphere, then the wavefront of light at time t dash frame will also be a sphere. Because all the laws of physics, all the laws of mechanics are invariant, as this is our postulates. So we have in S dash frame x square plus y square z square equal to c square t square, x square plus y square, x square plus y square plus z square equal to c square t square. This is the equation of a sphere, because equation of a sphere is x square y square plus z square equal to r square. So this is the equation of the wavefront in S dash frame, and similarly equation of the wavefront in S dash frame is x prime square plus y prime square plus z prime square equal to c square t prime square. This quantity x square plus y square plus z square minus c square t square is invariant under Lorentz transformation. We assume that, so x square plus y square plus z square c square plus t square equal to x prime square. As this is invariant under Lorentz transformation, we can write that x square plus y square plus z square minus c square t square. This is equal to x prime square y prime square plus z prime square minus c square t prime square. We have to use two postulates of relativity, as c is the same in all the inertial frame. In the law wavefront in S dash frame, this is the wavefront is sphere, and in S dash frame this will also be sphere, and the radius will be, and this is the equation will be same. We have written this equation in the two postulates of special theory of relativity. The homogeneity assumption of the space-time demands that two inertial frame will be completely equivalent, so the transformation equations must be symmetrical with respect to both, and if the quantities be finite, x prime, y prime, z prime must be also finite. So above condition requires that transformation equation should be linear, and with this consideration we can write x prime equal to gamma x minus vt and x equal to gamma prime x plus vt, x prime plus vt prime, x prime plus vt prime. Then after some calculation, we can find the value of gamma. We can find the gamma equal to gamma prime, and gamma equal, their value is 1 by root over 1 minus v square by c square. And putting the value of gamma and gamma prime, we can write x prime equal to x minus vt divided by 1 minus v square by c square, and y prime equal to y, z prime equal to z, and t prime equal to t minus vx and t prime. t prime equal to t minus vx by c square root over 1 minus v square by c square, y prime equal to y and z prime equal to z. These are the Lorentz transformation equation which is valid when the velocity is very less than c and also when velocity is comparable to c. And we can write inverse Lorentz transformation x equal to x prime plus vt prime by root over 1 minus v square by c square, y equal to y prime, z equal to z prime and t equal to t prime plus vx by c square by root over 1 minus v square by c square. The two sets of equations are symmetric with respect to all the kinematic relation valid for particle moving with high speed. And from this Lorentz transformation, we can get back our Galilean transformation when v is very less than c. From this equation, we get x equal to x prime plus vt prime, y equal to y prime, z equal to z prime and t equal to t prime, because this is part equal to 0 and this part equal to 0. And similarly from this set of equation, x prime equal to x minus dt, t prime equal to t, y prime equal to y, z prime equal to z. Another important point that in Galilean transformation, when the velocity of light is very less than c, then the space and time can be separated. But when the velocity is very comparable to the velocity of light c, then the space and time are not separable. We have to mention the 4 space-time coordinate of the event all together. The Lorentz transformation in this case known as special standard Lorentz transformation because we have taken the velocity of light in a particular direction. And this factor gamma, this is called 1 by root over 1 minus v square by c square. This is called Lorentz factor. This is called Lorentz factor. And we can plot gamma with function of v by c. When v by c equal to 0, the gamma will be 1 and this is increasing. This is the variation of gamma with v by c. And when v is greater than c, so gamma is imaginary, so real space coordinate, time coordinate are transformed to imaginary space. So maximum limit of the velocity is the velocity of light c. There cannot be any velocity, measurable velocity, which is greater than c, because in that case gamma will be imaginary and the real space time will be transformed into the imaginary space time. This is all for today. In the next lecture, we will discuss about the consequence of Lorentz transformation.